architecture that goes like this.
Okay. So where did we stop yesterday? So I wrote down some action which is good enough. I mean, it includes at least some ingredients of what I would like to study from the condensed matter point of view. You have metric, some scalar, which you can use to some bulk scalar, which is the dual of some boundary operator. It would be nice to be relevant, that you can use to deform the theory and introduce scales. And there is also the bulk gauge field, which you can use to introduce chemical potential, external electric fields on the boundary if you're probing the theory. And we said that if there is a fixed point, I mean, the potential V plays a crucial role on whether you have a fixed point or not, then the most general asymptotic solution that you can write close to this ADS boundary will take this form. So gamma AB, AA, phi S are the metric of, so gamma AB will be the metric on which you define, on which you have placed your conformal field theory. AA would be the external sources for the current operator, and phi S would be the source for the scalar operator. And we said how you could fix these constants of integration, HAB, which appears in front of the 1 over R D coefficient in the metric expansion. And similarly, for the gauge field, you have another constant of integration, JA. And similarly, for the scalar field, you have yet another constant of integration, phi V. Now, this is what we call the bulk action. And the crucial ingredient in holography, at least in the classical limit, in the strictly large N limit from the field theory point of view, is to say that the partition function of gravity as a function of these boundary conditions, gamma A, B, AA, and phi S, is actually equal to the partition function of the conformal field theory with the corresponding sources. And this is telling you that in the classical, in the strictly classical limit, what you can write is that the partition function can be approximated by e to the I and S. Here is the on-shell value of the action as a functional of gamma AB, AA, and phi S. However, what we mean by the S on shell is not exactly this action, right? So you don't take this action, you plug in the solution, and you have computed what you want. I'm not going to go through this in detail, but you need to add counter terms to this bulk action, which would regularize the theory, the bulk theory. Now, I'm not going to go into any details about that. There is very nice reviews. Maybe I can recommend a paper from the far past. 67. You can see how you can do that for models like this. But the bottom line is that, if you have the partition function, you can find the generating functional. You can start taking functional derivatives with respect to the sources. And what will end up happening is that the dual field theory stress tensor is going to be given precisely by this constant of integration HD. And in fact, the precise value would be D times L times HAB plus potentially a term which is a local function of the sources. So that would be basically contact terms. Right? So after you find the full solution to the bulk problem, this HAB would be a non-local function of these sources, This is where all the interesting stuff is happening. But because you have these counter terms, you can have contact terms, which could be local functions of the sources. Okay, so I'm mostly going to be interested in this piece. However, if you want to be super careful and you care about supersymmetry and other things, this plays a big role. Okay? Now, for the dual current operator, I can write down something very similar. You would have a factor of d minus 1. I would need this constant of integration JA, plus, again, potentially contact terms in the sources. Okay, so these are all local terms. And for the dual scalar operator, you have a similar story, but the non-local term will be given by phi v, that constant of integration, plus, again, local terms in the sources. And usually the nice thing about working in 4 bulk dimensions for d equals 3 is that you can actually show that this xab and this ca are just trivial. They are 0. Okay? The trick is to bring everything in Pfefferman-Graham. When you do that, even asymptotically, it doesn't have to be everywhere in the bulk Pfefferman-Graham. You can find a coordinate system where the GRA and the GRR components just fall off with R sufficiently fast, and then you are in a good position. Okay. Right. Now, this, I think, concludes what I want to say about the UV part of the story. Right? So this is how I'm fixing things. This is how I read of things. And now I want to tell you about fixed points in holography in gravity, which are of interest in condensed matter physics. So let me call these fixed points z greater than 1. Okay, so the UV fixed point had z equals 1. It is about a CFT, a relativistic conformal field theory. Okay, so what was the nice thing about ADS? So the nice thing about ADS is that it was geometrizing, I don't know, Lorentz symmetry, scaling symmetry, and the special conformal transformations, right? So when I'm in Z greater than 1, the symmetries that I want to preserve are what? So the symmetries that I want to preserve are basically Euclidean rotations. Euclidean translations and time translations. And the other thing I want to preserve, just to make sure that I'm looking at the fixed point, is that there is a scaling symmetry with dynamical exponent z. So I want to make sure that whatever I write down has the following as a symmetry. Okay? Now, in ADS, or for the relativistic CFTs, up to here it was almost trivial. But what really mattered was the existence of an extra coordinate r. Okay, so in the z equals 1 case, I scaled time, I scaled space, and I scaled r at the same time to have the symmetry. So just by mimicking this story, the kind of geometries that I'm interested in would have a metric like this. So ds squared. Something like this would work. All right, so all I have done is to take ADS, take this exponent, and change it from z equals 1 to just z. Okay? So you can just check that if in this transformation I also add that the radial coordinate goes to lambda to the minus 1 r, then this metric has this symmetry. Okay? But as you will notice, well, I would like this to be symmetry of all the matter fields that participate from the bulk point of view. Okay? Now, in the case of ADS, if I had a vector or a scalar, there was nothing non-trivial that I could write about those two objects that would be invariant under this. Well, with z equals 1. Okay? And with Lorentz boosts. I don't have the Lorentz boosts here. However, in this case, I am allowed to write something for the bulk vector field, which is again invariant under these transformations. And if you think about it, yes, there has to be some matter field which will tell you exactly what is breaking this Lorentz symmetry in the bulk, from the bulk point of view. So you do need a vector. Something has to break this symmetry between x and t. And that is a vector. Now, for phi, there is nothing you can write, right? That could be invariant under these symmetries. So phi should be some constant. So these bulk fields have, this Lifshitz symmetry. This scaling symmetry is called Lifshitz symmetry. They have Lifshitz symmetry as an honest symmetry. Okay. Now, okay. So what kind of theory can have this as a solution? This is now the next step. So a theory which has this as a true solution, I will write down the minimal thing. You can add all bells and whistles here. I mean, you can add anything you like. But the minimal thing that you need to have in order to have this as a solution is, of course, a metric, a cosmological constant, a gauge field, which is not a gauge field. It is a vector field. You need this vector to be massive from the bulk point of view. So you don't have anymore the gauge symmetry from the bulk point of view. Okay? Now, let me write the relation between the bulk theory parameters and this z or whatever appears here. So lambda, the cosmological constant, is related to d and z in the following way. You have some expression. I hope what I write is correct. Okay. Now, the mass of the vector field is fixed by z and d. Well, I'm not sure this is the appropriate way to read these things. I would like to write z and l as a function of the bulk parameters. But if you want to cook up some theory which has the specific z, this is what you need to do. I mean, you have to write down some bulk action like this. I am an advocate of the other way. Yes?
Do we care about that?
Let me write down my last equation.
Okay.
Okay? So the last equation that I want to write is this one. So what is this C? Okay? So this C has C squared is 2 times 1 minus 1 over Z. Okay. You can take ADS and you can have a massive scalar, but it will be 0 on ADS in the Z equals 1 case. Does that make sense? The A field, yes, I think we're talking about the same thing. So A has a C. Okay? Good. Is everyone clear with that? Yes, okay. Good, so okay. What happened here? So this is telling you that you can have this Lifshitz scaling as long as the bulk gate symmetry has been broken. Okay? And how do I end up from something like this to something like this? Well, I'm writing down here the minimal thing. You can probably imagine that apart from the scalar phi there, I had also a charged scalar under the gauge field. The charged scalar took it took a non-trivial value, and this is what gave mass to the gauge field. So these geometries will be there, and they have been found as infrared fixed points for superfluids, for example, where the U1 symmetry has been broken. Okay, so this is what will happen in the IR, from the IR point of view. Okay, this is now as far as the geometry goes, but maybe I want to run a quick argument to see how, let's pretend for a while that I'm only interested in the IR fixed point, that I could do holography with the IR fixed point without the UV part of the geometry. Let's see, really, why would correlation functions scale in the right way in this geometry? The geometry has this symmetry, but somehow I also want to show that the retarded Green's functions will have, the right symmetry. They would scale like this. So if I had some boundary operator psi, and I would scale the frequency and k, that I would basically get scaling like this. Okay, for that, I need to consider fluctuations on top of this geometry. So let's do that. However, to do this problem, you really need to start adding counter terms and yes. Oh, it's -2 plus eta. And eta is related to the dimension of the operator psi in this way. It is 2 delta, what? Minus z minus d plus 3. Okay, so okay, so to do this properly, you would have to take, I don't know, some bulk action and do the holographic renormalization with respect to the ADS fixed point, not the UV fixed point. I can probably write a couple of papers which have done that for these Lifshitz geometries. There is this, if you want to have a look. Okay, so what's the simplest thing I can consider in terms of fluctuations? So let me just take a bulk scalar. Right? I will take some bulk scalar. I will call it phi, but it's not necessarily, the phi that you have in the background. It's some scalar with a mass term. Okay, and now this box is with respect to that metric. Right, so you can Fourier decompose. You have, again, translations in time and space, so it makes sense to Fourier decompose in t and x. You can write the field phi like this. You can pull out an exponential. times a function of the radius. You can plug this in the Klein-Gordon equation, and what you will find is a radial equation for f. So you will have r squared f double prime plus z plus d r f primed plus omega squared divided by r to the 2z minus k squared over r squared minus ml squared times f equals 0. Now, the first step you could do in ADS, you could study the asymptotics at r goes to infinity. You want to do the same thing. I mean, r equals infinity is a singular point of this equation. You can write the Frobenius expansion. And the two constants of integration that you could find goes like this. So you could have some constant f naught times 1 over r to some power d, capital D, minus delta, plus whatever, plus another constant of integration, f1, then 1 over r to the delta, plus whatever. Now, I have defined an effective dimension capital T, which is d plus z minus 1. So for z equals 1, this is exactly the dimensionality of your dual field theory. In this case, I have to define something slightly different. And this scaling dimension delta in this case would be very similar to what you could write for ADS. This is capital D. Sorry, my delta and my D look very similar. That should be equal to ml squared. Okay? Now, according to this logic, f naught would be the source from the boundary theory point of view. Now, the vev of phi would be proportional to this constant of integration f1 plus contact terms in the source f1. Now, if you want to read the details and see what these contact terms are, maybe you can have a look at this paper. Okay, so the goal, I don't want to solve this equation. I only want to show you that whatever the solution is, it will have the right, it will give you the right scaling symmetry. Okay. Now, where is this scaling symmetry useful now in this equation? How does it reflect? How does it show up in this equation? So now I want to define a new radial coordinate. I want to define rho by using omega. Okay? And now the scaling symmetry of this equation, okay, I want to define this rho, and I also want to define a new function. So, and g of rho, which is just f of omega to the 1 over z times rho. Now, if I make these transformations in this equation, I will find an equation for g in the rho coordinate, rho squared, g double prime, plus d plus 1, rho g primed, plus 1 over rho to the power 2z, minus k over omega to the 1 over z, and all that, sorry, no, then rho the minus 2, minus m squared, L squared, times g equals 0. Okay, so I have brought now my equation in the form where the solution for g can only depend on this ratio and this dimension. Okay, it can only depend on these two parameters. So the asymptotic expansion for g would be some number g naught times 1 over rho to the power d minus delta plus something plus g1 times 1 over rho to the power delta. Okay, so if I compare the two expansions, then I can compare the two sets of constants of integration, and I can say that f naught, the constant of integration, this is what I'm fixing actually, right, from the boundary theory point of view. I'm not fixing that. I'm fixing that. So that constant of integration would be omega to the power d minus delta over 2 times g naught. And the second constant of integration would be omega to the delta. Sorry, this is z here. Times g naught, times g1. So what do I want to tell you? If I keep looking at the g solution, so if I specify the constants, I mean some relation between the ratio of g1 over g naught, that will also specify the relation between f1 and f naught. And that's the retarded Green's function. That's exactly what I'm looking for. Okay? So the last thing that I still need to make sure is that everything is regular as r goes to 0, that I have infalling boundary conditions. So if I look at the singular point rho equals 0 in this equation, I will find two behaviors. I will find that as rho goes to 0, then the function g of rho would go like rho to the 1 minus d over 2 times some constant of integration e to the I over z, rho to the minus 1 plus whatever. And the second constant of integration would be c2 times e to the minus I over z, rho plus whatever. Okay, so this behavior satisfies ingoing boundary conditions on the at r equals 0, and this behavior is like outgoing boundary conditions. So I definitely want to set C2 equals 0 here. Okay, I want stuff to be just falling down the singularity. But let's pretend that I have set C2 equals 0. Then, in terms of the g function, you know, if I set, let's say, g naught equals 1, then g1 can only be a function of these two numbers. Okay? So this is telling me that, I mean, the form of this equation is telling me that g1 over g naught can only be a function of k to the power z over omega and the dimension. I mean, the dimension of the operator comes through the dependence on the mass. Okay, so, but what I'm actually interested in is f1 over f naught, which if I use that relation over there about the change of coordinates, that is going to give me omega to the 2 delta minus d over z times the function f. Okay, which is exactly what I wanted to see happening. This is proportional to G. Okay?
Can I ask a question?
Yes.
Something I missed. So in the previous case, not in the Lifshitz case, you are assuming or finding a UV with ADS and then some smooth ending of the space occasionally, right? Which you were asking this in boundary conditions for a probe. In the Lifshitz case, tell me if I misunderstood this, you said that the ADS point could be in the infrared.
No, I'm just looking at the infrared, which is the Lifshitz geometry.
Okay, but then what we call, so now you are putting this probe on the Lifshitz geometry.
Okay, yes.
What do you call infalling? There is infalling into where?
To the, okay, Lifshitz at Z equal, at R equals 0, it has a singularity.
Okay.
Okay, so
Okay, so
I
it's
want
infalling
stuff
there.
to just be falling towards the singularity. Nothing should be coming out.
Good. And you will live with that singularity. In the other case, you are asking for not to have a singularity. In this case, you will have to live with that singularity.
So yes, these singularities will be masked by finite temperature, finite temperature horizon. But as I'm changing the limit of small omega, small temperature, this scaling should start showing up in a small temperature limit.
All right. Thank you.
No problem. Yes.
You said that the Z equals 0 limit is a bit interesting, like
Z equals 0.
Yeah, everything starts kind of almost looking like 2D. Is there any?
So for Z equals 0, I think the complex field would, the gauge field would become complex. I'm not aware of any solution that would have Z smaller than 1.
Oh, okay.
It is always Z greater than 1.
Okay.
Okay, good. So this is what happens with the exact Lifshitz symmetry. Now I want to go back to the original theories that we were looking at, which had an exact gauge symmetry, and look at potential fixed points without having a broken gauge symmetry in the bulk. Okay, so now I want to look at what is called hyperscaling violating fixed point. Well, they are not really fixed points. But they can give you interesting phenomenology. So once again, we're considering the bulk action, which has the metric, some scalar, I also want to pull out some factor of 1 over L in front of the L squared, in front of the potential, some coupling in front of the gauge field, like this. So now, I want to look for general fixed points in theories like this, without any breaking of the gauge symmetry in the bulk. Okay? So what we learned from the Lifshitz example is that I can probably look for solutions. Let me write down the most general thing that would preserve all the symmetries that I wrote there, apart from scalings. Okay, I want to actually make sure that I'm not missing anything that holography can give me. Okay. For the gauge field, I can write something as a function of this radial coordinate, you know, that breaks Lorentz symmetry. And why not write down some ansatz for the scalar, which does indeed depend on R. Now, this is an ansatz that will give us many things. So I want to write down the ODEs that you would get from just solving Einstein's equations, the equation of motion for phi and for the gauge field, if you plug in this ansatz, right? So so the log of the derivative of the log of g is r over 2 d minus 1 phi prime squared equals 0, and r to the minus d plus 1, r to the df primed plus 1 over d minus 1 gv plus z over 2g v prime squared equals 0. And the equation, Maxwell's equation will give you some equation for P. And finally, the equation of motion for the scalar would give you some equation in the radial coordinate for phi. Okay? So if you write down an answer like this, then you have to solve this system of ODs. It might look messy, but I want to do something simple with it. Now, as I told you, you're looking at theories which come from supergravities. And now I want to look at potential, behavior that you can identify from the low energy point of view, you know, in a theory of supergravity. Now, what happens quite often is that this scalar phi becomes quite large. And in the large phi limit, v behaves like minus some constant times some exponential of phi. Okay, this is when phi is large. It's a large number. This is a limiting behavior for this potential. Similarly, for the function z, you have some exponential behavior, usually. Z of phi grows like z naught. E to the alpha over 2 phi. Okay, so if you take this limiting behavior in these equations of motion, you can actually find simple solutions for these functions that I have there. What would give me the Lifshitz geometry would be, you know, power law behavior in the radial coordinate. So I can look for similar power law solutions in these functions f, g, p, and phi. Now, to write what I can find,
Can I
given...
ask a couple of questions?
Yes.
Something that I'm missing. With the last equation, I'm okay, same with that one. The F and G, they seem to solve first-order equations.
Yes.
Why is that? So shouldn't one expect that one of them at least is second order? These are
Okay,
Einstein's
there is
equations,
also a second-order equation, which follows from these first-order equations.
Okay. All right. So
Basically, this is not an accident. I mean, it's the Bianchi identities. If you make a reasonable ansatz, then this is bound to happen. You will get higher-order equations, lower-order equations, and the higher order should follow from the lower order.
Good. And the other question is, you will not impose anymore that the V has a fixed point solution. Right?
Now I'm just looking at what can happen in the infrared limit.
Okay, all right.
So I'm telling you what happens when phi is large. Phi is not large close to the boundary. I'm now moving away from the boundary. Yes. Yes. No. I can wait.
But in a large phi limit, why does V scales with a negative exponential in phi? Is it does it explode exponentially or?
I didn't say beta is positive.
Okay, you didn't say that. Oh, fantastic.
Okay, good. Okay, so to write the solutions that I find in a more humane language, I want to define a couple of numbers. So theta is a number which is d minus 1 squared. This is horrible, sorry. Over alpha plus beta d minus 1. And then I want to define the z, which is 1 plus theta over d minus 1. Plus, okay, sorry about what you will see in front of your eyes. D minus 1, d minus 1 minus theta, plus theta squared, divided by d minus 1 squared, and then d minus 1 minus theta times a squared, alpha squared. Right, so what I want to tell you is that these exponents, beta and alpha, can be traded for some numbers, theta and z, okay? Now, I have things in a quite complicated way. Let me simplify things as much as I can. Okay, we have defined this. Now, I want to define a new radial coordinate.
Sorry?
Yes.
This set is the same as the set multiplying the f
No,
squared?
that's little z. Thanks for asking.
Ah, okay.
Ooh, see what can happen, yes. Yes, that's little z. Okay. That's more like the dynamical exponent. This is just a function.
Ah, okay, I see. Okay, thank you.
Any more questions like this, especially like this? Okay, good. Now I will define some new radial coordinate that will make the solution look simpler. So I will trade r over there for some coordinate rho, which are related in this way. And what else? I will also scale time like this, 1 minus theta over d minus 1 times d tilde. So this G naught and P naught will appear shortly, what they are. And I'm also going to scale the x coordinates like this. G naught over P naught, some power 1 over z, times 1 minus theta over d minus 1 times xi tilde. So if I define these new coordinates, then, and I plug in the solutions for these functions g, f, p, phi, then the metric I'm getting is this. So I will have that ds squared is some number L tilde squared times rho over rho naught to minus 2 theta over d minus 1 times minus some constant of integration p naught squared times rho to the 2z dt squared plus rho squared dx squared plus d rho squared over rho squared. And for the gauge field solution, I will have P A naught, P0 A0 times rho over rho naught, the d minus 1 minus theta times rho to the z dt. And the scalar will have this dependence, 2 d minus 1 minus theta, d minus 1, z minus 1 minus theta, over d minus 1. And then I will have a log of rho over rho naught. Okay, so what are the comments I want to make here? So in the process of solving for these functions, I have discovered two constants of integration. Okay. So the first constant is this P naught. So what is P naught? Well, P naught scale sets basically the scale of time, okay, in this infrared geometry. I can just get rid of it just by redefining time. That's okay, that's benign. That's not a bad thing. The second constant of integration that I have discovered, which is not so innocent, is this constant rho naught. Okay? And if you see this rho naught is a scale that is set in this theory and which precisely violates any scaling symmetry that I can have either in the metric. You see this factor in front actually spoils the Lipschitz scaling symmetry that I could have just by this factor. Okay, so there is an additional scale which survives in this fixed point, which makes it not a fixed point, precisely because there is this scale, and it is telling you that things are still running. You have not converged to a fixed point. That's still an interesting thing. Okay, so this scale rho naught will basically carry information about the UV theory. Okay, you cannot decouple this from your UV fixed point. Okay? Now, the fact that the matter fields are not invariant under scaling tell you that, you know, some correlation functions could scale with omega and k. Some other correlation functions might not scale at all. Some other correlation functions might have anomalous scaling. It depends on how your bulk fields, your perturbations, are actually coupling to functions of this background phi. Okay, the equation that we solved before about Lipschitz geometries had an exact scaling symmetry. And this is what helped you show that the correlation functions from the boundary point of view will have this symmetry, will inherit this symmetry. The fact that I have background fields now that do not have this exact symmetry is telling you that, yeah, you might have it or you might not have it. So there will be anomalous scalings in these infrared, not fixed points. And this is why we call this hyperscaling violating geometries. Okay? Is there any questions you have at this point? Yes?
Yes, I want to be clear. Why you mentioned that factor rho naught is the responsible for
this one here?
Yes.
Yeah.
you mentioned that is the responsible for the this violation of the Lipschitz symmetry. Is that right?
That constant of integration, right? That extra scale that appears in the problem.
Then solutions of that type can and cannot have this Lipschitz symmetry.
Well, you see, let's cook up a theory. The problem is bigger than just this factor, okay? Let's cook up a theory which has theta equals 0. Let's make this disappear. The problem is still there because of this extra factor in the Gates field, for example. Or this guy, the scalar, will keep running, even if I set theta equals 0 here. So to get an exact symmetry, you definitely need to break the Gates symmetry in the bulk. If you don't break the Gates symmetry in the bulk, you will get stuff like this. This is what I'm trying to say.
Okay.
And thanks for the question.
Okay, thank you, thank you.
Yes.
Okay, I have two quick questions first. All the z's here are the dynamical z, right? It's not the little z. Just to confirm.
This?
Yeah, all the z's here.
Oh my God, yes, sorry. This Z is this Z.
Okay, yeah. No, yeah, I imagine, just to confirm.
Yes.
The second one is, why do you care about it again? Like, what are like the specific systems we're trying to describing? Like, any class of systems condensed matter that behave like that?
With this?
Yeah, the hyperscaling violation, or just the hyperscaling behavior. General.
There is examples of systems which, for example, you will see this bad player theta coming in. So just by, scaling arguments, you can say that if my zero temperature system has this scaling symmetry, then thermodynamics should behave in a specific way. For example, entropy density should scale with a specific power of temperature. There is condensed matter fixed points. I'm forgetting the examples where entropy does not scale in the right way. So you do have some violation of what you would expect.
Okay, thank you.
No problem. Any more questions? Yes.
All these systems of equations you're getting by imposing that your configurations will be the higher dimensional equations of motion, right?
Okay, good. I'm just writing some lower dimensional theory here with some V and Z, right? So for any theory that you can write down, for some V and for some Z, these are the solutions you need to solve. What the dimensional reductions from higher dimensional supergravity would fix is the precise form of V and Z.
Yeah, the solution of these equations.
Right. But what I wanted to say is that all dimensional reductions that I know of for large phi have this behavior.
Oh, okay. Okay, thank you.
I think maybe it's good, I have it somewhere. I have somewhere an example. Well, later I will write down specific examples about the dimensional reductions, and the values of theta and z you can actually get from, 11-dimensional supergravity, for example. Okay, so this is just the kind of hyperscaling violating geometry I could have as a fixed point, but I want to be able to connect it somehow to the UV fixed point, right? So, as an IR geometry, as an infrared geometry, this is fine. It is just sitting there, but somehow I want to connect it to ADS, right? So in order to connect this to ADS, I need to study static modes, extra constants of integration that I have actually set equal to 0 here, that will let me escape from this geometry and just go to the UV fixed point, right? So what would you have to do So I want to write down a few things about static perturbative modes around this geometry. Okay, so what do I even mean? So I found some background solution for this function f that I wrote in my ansatz. So now I want to take f of rho to be the background solution that I found, fc, plus some perturbation in f, which is a function of rho. Okay, and I want to do this, I want to play the same game with all functions. I want to play the same game with P. The background solution, which is basically that. And the same thing for phi. So you plug this thing in these equations of motion, you expand in delta phi, delta f, delta g, delta p, delta phi, and you're trying to find solutions for these functions. Yes?
Are these hyperscaling violating configurations more general than the Lifshitz configurations? Or
Well,
in some sense, are these included in the Lifshitz?
Okay. I think, yes, it's good to ask this. I think I tried to explain this before, but let me try again, okay?
Okay, sorry.
Good. No, it's not your fault. It was definitely my fault. All right, so even if I set theta equals 0 here, right, and the metric does look Lifshitz, there is still a problem with, let's say, phi. If I set theta equals 0 in phi, it's still a function that depends on r. So even if the metric is Lifshitz, the scalar field does not respect the symmetry, even for theta equals 0.
Okay.
Okay? So the problem here is that I have not broken the bulk gauge symmetry. My vector field is not massive. The theory that I wrote down doesn't have a mass.
Okay, I see.
Okay, so even if I get some geometry that looks like Lifshitz, the matter content will not have this symmetry.
I see.
Okay? Good.
Okay, thank you.
Okay, so you want to, well, I want to plug this in these equations. It's expanding f, g, p, phi. And what you will get is a big mess. It is a big mess unless you write this function f like this. So there is some constant of, some constant f naught coming from the background. So I want to write the perturbation in a special form. So this part, what I'm writing down, is the background. Okay? So I want to write the perturbation in the way that there is some constant Cf, and then some power delta. Okay? So this piece times that is what is delta F. And I want to expand things in epsilon. Of delta, yes. Okay? Let's do it like this. I will do something similar for G. So we'll write the background exponential z minus 1 minus theta over d minus 1. I will have a 1 because that's the background, plus epsilon times some number, again, rho to the delta. And for P, I will write the same thing. There is the background thing. I will have a 1 plus epsilon, some constant Cp, rho to the delta. And similarly for phi, I will have this ugly square root. Well, you know, it's that square root over here. Let me call this, I don't know, some number, W or phi naught. Phi naught times log of rho over rho naught, that's the background, plus epsilon c phi rho to the delta. So you see that I have fixed these exponents here somehow. I mean, no one told me to do that. But the reason why I fixed my exponents like this is because if I plug this perturbation in these equations of motion, then the resulting equations of motion will take this form. There will be some matrix which is a function of this delta times the vector of constants Cf, Cg, Cp, C phi equals 0. Okay, so if I choose these exponents to be like this, then I can write a consistent system which is just a matrix independent of rho times the constants of integration. Now I want to find a non-trivial solution of this system, and in order to find a non-trivial solution of this system, this should be a non-invertible matrix, right? So setting the determinant of this matrix to 0 is what gives you these exponents. So this is telling you now that the determinant of m of delta should be equal to 0. Now, how many solutions should I expect? Okay, there is only one derivative in G, one derivative in F, so that brings down 2 powers of delta. So that would be a polynomial equation that I need to solve in delta, right? I have a second derivative in P and a second derivative in phi. So that would be a 6th order polynomial to solve in delta. And that would give me 6 different modes, 6 different static modes. Okay, so what are these modes? I don't want to erase that, but I did it. So let's look at these 6 modes. So this leads to 6 modes for delta. And so I have 2 distinct modes with delta equals 0. Okay? That would have been easy to guess. You see, we had 2 constants of integration, this P naught and this rho naught. So these static modes, all they do is just change the value of these 2 parameters. Okay? So that's expected to happen. Now, there is another pair of modes. And I want to call them, I think I want to call them delta plus minus. Okay? So those 2, the exponents of those 2 modes add up to theta plus 1 minus z minus d. And they can also be written like this. So delta plus is 1/2 theta plus 1 minus d minus z plus a number nu phi. And delta minus would be 1/2 theta plus 1 minus d plus z minus nu phi. Now, I don't want to write down what this nu phi is. I will probably upload my notes. You can have a look at it and close it forever. The point is that this number is positive, and this number is negative. Okay? So what does this mean? So let me look at this behavior here. If I go back and I look at this expansion, is that the mode with delta minus is negative actually destroys the IR part of the geometry. Right? So the IR part of the geometry is as this rho goes to 0. So if I want to connect this to some UV fixed point, it better be that this mode does not exist in this expansion. It's set to 0. However, the mode with delta plus is positive alters the UV part of the geometry. Okay? So turning on this mode with delta plus positive is actually going to keep your IR, because your IR is at small values of this rho, but it's going to change the UV part. So it might let you connect to some UV, to some ADS solution in the UV, right? So the pair of these two modes, they represent, you can think of them as being the VEV and the source of any relevant mode from the IR fixed point of view. Okay, and you definitely need to set the VEV of the operator equal to 0 in the IR fixed point. Okay, how many modes have I talked about? 4. There is 2 more. And these are very nice modes. I like them. So there is another pair of modes, okay? And let's see what these modes are going to do. So there is another couple of modes with, I want to call them delta t, which have theta plus 1 minus z minus d, and this is negative. That's a negative number. You might want to check the following. If you manage to find these modes, they do a couple of things. The first thing is that, you see, I'm solving for these modes by linearizing everything, okay? Now, there is a nice observation about these two static modes, is that they are solutions to the full nonlinear problem. Okay, so even if I linearize, I'm finding the exact solution. I don't have to do anything else. The second thing I want to emphasize, I haven't talked about this too much, about the dimensionalities, is that, okay, so if I set this power delta t here, then immediately these constants of integration acquire some dimensionality, okay? Now, the dimensionality of these constants of integration corresponding to this exponent is that they have the dimension of energy. Okay, and someone who has been following what I'm saying, they might revolt in the following way. Look, And you could say that here you had some negative power, and you said, I don't want that. Okay? Yes, this has a negative power, and if I add a negative power here, everything will just run away in a singular way. Okay? I will not get something nice out of it. However, this power also has a negative, this is also a negative power, but, and they do change the IR part of the geometry, but in a very nice way. They actually create a small black hole. They introduce a horizon in the geometry. Okay, so these two modes can be used, as we will see, to heat up the solution. So if you take these nonlinear solutions and you plug it in here, what you have constructed basically is, without, I'm imagining that I have not added the irrelevant mode. Let's only add these two modes. So what I have constructed is a black hole solution or a black brane solution, which has this hyperscaling violating geometry as its asymptotics with a black hole horizon. With a horizon, okay? Yes. Okay. Say that again?
What do you mean by non-linear?
I mean that they solve these equations exactly. Before, yes. So if you take the background solution, which is this part, okay, you find the right constants by solving this problem for this value of delta, and you plug it in here, that will solve actually that equation, that system of equations, without expanding. These are the finite temperature versions of these backgrounds. Is that clear? Good. Okay. So we are going to look more into that when we discuss finite temperature. Now I want to, I think, talk about RG flows, which should be somewhere here. No, it's not here. Anyway, I think I can start talking about it. Okay, this is how we are going to heat up our solutions, but I still want to solve the problem of RG flows at 0 temperature, okay? Let's not talk about finite temperature yet. So the first type of RG flows that I would like to discuss are just, RG flows that go from a relativistic CFT to another relativistic CFT. This is the simplest thing you can think of. You just have a UV fixed point. You have a relevant operator with respect to that UV fixed point. You put a scale, a number, and that triggers an RG flow. And you hope that there will be an infrared fixed point in which your RG flow is going to terminate. And then, yes? Oh, I'm thinking of, having just a relativistic CFT. Oh, you don't want me to erase that? Okay, yes. Okay, I can keep that. Yes?
A simple diagnostic that tells you that it came from our G flow from a relativistic theory? Is that a special subclass of theories that have special features?
Well, right. So if you just examine, okay, you have your fixed point, your Lifshitz fixed point, then you want your operators to give you enough irrelevant deformations to possibly connect to some UV fixed point. And that you can tell just by looking at the action.
But that seems complicated because you need to know the full operator spectrum and some other. Aren't there other diagnostics that you? Somehow intuitively, the fact that you have this general relativistic theory that's dual to it seems to suggest that if you turn on an epsilon irrelevant deformation, you should already start to see a hint of relativistic physics. Somehow, I don't know exactly how, but.
You mean even without having the full RG flow, right?
Yeah.
I haven't really thought about that. It is a good question.
Yeah, I was always wondering if this is yeah, okay.
No, but yeah, that's yeah. There might be a diagnostic which tells you that yeah, you are going to actually flow to something relativistic, in fact.
Because people have also discussed having things like this with some neutron-Cartan type theory in the bulk, and then there might be other things possible. So there should be some distinguishing feature, right? So
yeah, exactly. Yeah, I'm always having in mind relativistic theories from the boundary point of view. Yeah, but yeah, flowing from something non-relativistic is another possibility. Yeah. Right. I think I have my notes somewhere in the cloud, but not on paper. That's not a good idea. Well, okay, I can probably give you a quick introduction before I find them. Right. So let's talk about RG flows. Between relativistic fixed points. Okay, so the minimal thing that you need in order to discuss these flows is the following. So you would definitely need the metric. Right? And you would also need an operator, a scalar operator that will trigger the RG flow. Okay, so let's put in a scalar. And that's it. That's a minimal thing. So now to have two fixed points, there is some requirements, right? So the existence of two fixed points is telling you that V of phi should have two extrema. Okay, so there should be two solutions to V phi primed equals 0. And let's call them phi UV and phi IR. These should be constant values of phi that extremize V. Two different values, two different extrema. Yes? Exactly. And now I'm planning to tell you what will distinguish them. What is the UV, what is the IR, right? And of course, the values of these two extremas should both be negative so that you will get an ADS fixed point. Okay? The values of the potential at the two extremas would give you the cosmological constant, okay, which has to be negative. Good. Now, the next thing is that the mass squared in the IR, okay, before writing that, then the radius of the IR ADS would be minus d minus 1 over the value of the potential at the IR fixed point. And correspondingly, the radius of the UV ADS fixed point would be given by the value of the potential at the UV fixed point. Now, what makes these two fixed points an IR and a UV fixed point is the following. So if you look at the bulk masses of the scalar phi around these two vacua, then they are simply the second derivative of V in the IR. And correspondingly, in the UV, it would be the second derivative of the potential in the UV. Okay? Now, the masses of the bulk scalar around those two fixed points is exactly what fixes the dimension of the dual operator. Okay, so you know that delta IR times delta IR minus D minus 1 is equal to M IR squared L IR squared. And correspondingly for the UV, you will have M UV squared L UV squared. Okay, so for the UV fixed point to actually be a UV fixed point, M squared should be positive, okay, so that you would get an operator of a dimension greater than D. Okay? So delta UV should be greater than D, which is telling you that MUV squared, sorry, I'm saying things the other way around, yes. So delta UV should be smaller than D, sorry about the confusion, and it should be greater than D minus 2 over 2, because you want the UV fixed point to be stable, okay? So MUV squared should be a negative number, and it should be greater than D squared minus D squared over 4. Now, what makes the IR fixed point an IR fixed point is that delta IR should be greater than D, and which is telling you that MIR squared should be a positive number. Okay? Yes? Exactly, exactly, yes. So that the phi operator from the UV point of view is a relevant operator, right? And correspondingly from the IR point of view, it's becoming an irrelevant thing. Okay. Now I think I'm starting to need my notes. Good. I will write the system of equations that you get. Well, you want to write an ansatz for the metric. Now, an ansatz which is good enough for the metric is the following. So it is it is R squared eta AB dxa dxb plus the R squared over R squared U. What is the logic between these, behind this ansatz? Now, and phi, of course, is going to be a function of R. Now, the solution that I'm after, okay, what should it do? Why, I mean, what would be a flow? What would make this a flow? So if I imagine that the UV fixed point is at large values of R, and this is what should happen if I write my metric in this way. So for R goes to infinity, this function U of R should go to what? It should go to the radius, to 1 over the radius of the UV ADS squared. And correspondingly for R going to 0, U of R should go to 1 over the radius of the IR fixed point squared. Okay, so in the UV, I'm getting the UV theory. In the IR, I'm getting the IR fixed point. That's what it does. It's as simple as that. Now, from the point of view of the scalars, there is only one scalar, what is the asymptotics? How should phi approach these two values, phi UV and phi IR? So for the scalar, for large values of R, phi of R should be, I mean, it should approach the UV value, right? And what else? There will be my two friends, the deformation and the vev of the scalar. So I should have the source of the scalar in the UV divided by R to the D minus delta UV plus stuff that will be determined in terms of this constant times phi U UV over R to the delta UV plus other stuff which is determined in terms of these two constants. Okay? Now, as I'm going to the IR, I am going to have a similar expansion. And you can see, I mean, sorry, before I go to the IR, you can see that if the operator is relevant, which means delta UV is smaller than D, then as I'm taking R to infinity, both of these terms just fade away. Okay, they just go to 0, and I'm getting back my value phi UV, which is what I want. Now, from the IR point of view, I'm going to have a similar expansion. I'm going to have the source term from the IR point of view divided by R to the D minus delta IR plus other stuff. And I could, in principle, have this, the vev from the IR point of view. Now, this term, as long as the IR operator is irrelevant, which brings you here, and as I'm taking R to 0, it just fades away, right? It is an irrelevant operator. However, this term would destroy my IR solution. It would tell me that this is not the true IR theory that I'm after. So I would definitely want to have this equal to 0 in order for that fixed point to be the true infrared solution. Okay? Good. So the strategy is to just take these ansatz, plug it in the equations of motion, and come up with a solution that satisfies this. I'm hoping to do this next time. I will tell you how it works because I need my notes. Good, but yes. So for this example, I think I'm going to send to the organizer, to the secretaries, a Mathematica file which does all that. You can see this expansion, how it works, how all the terms are fixed in terms of these constants of integration, how you construct the full flow. It's a nice thing to see. You might never want to do this in your life, but it's good to see it working because all you hear from me is just words. You will not see this solution, okay? You will see how that solution should work. Mathematica will tell you that, yeah, okay, there is some solution. Okay? Thanks.
More questions?
Just, I got confused with the names of the modes because I don't know if I remember, but you call the second mode the one that is erased.
This one?
Yes, irrelevant, but I thought that was important because that breaks the UV part. What that?
So if I want to think of this fixed point as an IR fixed point, I definitely want to destroy its UV part. And I want to go somewhere else, but I want to keep the IR part, which is the small rho region.
And that's why it's irrelevant.
Say it again?
That's why it's called irrelevant.
Yes, exactly. That it has the potential to change the UV part of the geometry, but maintain the IR part.
Okay. Okay. And the other question is more general.
Yep.
Why we want to go from one configuration to another with this exercise? What is the objective?
Oh, okay. So this simpler exercise is just to tell you how an RG flow would work in holography, right? I mean, in a simple setting with no chemical potentials, no breaking of the Lorentz symmetry, nothing like this.
But that flux, what does it mean in the holography? This exercise in the bulk.
Mm-hmm.
What does it mean in holographically?
In the CFT. Oh, that I have introduced. I have my CFT, right? I took this operator. I just introduced a dimensionful number in the CFT, and that will just change the low energy dynamics of the theory, and it will make me just go to another CFT
Okay.
when I look at long wavelengths or very small frequencies.
But experimentally, it has an importance.
Well, I mean, from the theoretical point of view, you would like to just take some UV fixed point and end up with another fixed point, right? So there's, I mean, the RG flow has to terminate somewhere.
Okay. Okay. Thank you.
No problem.
Any more questions?
The expansion for in the IR doesn't seem to be very controlled because it seems like it should be a very good large R expansion, but not a good small R expansion.
What do you mean it's not under control?
So maybe I don't know, maybe I'm thinking about this wrong, but I thought this expansion was good when R was very large. The expansion for phi.
You don't think the expansion is good?
Although the UV one I agree. I don't know about the IR one.
It's exactly the same expansion.
Even for small? Okay.
Yeah. I mean, it doesn't matter. It's linearized perturbations. You do exactly the same thing.
Okay, thanks.
There is one question in the chat. You can read it there.
Oh, it's just linearized perturbations again. It's just fluctuations around ADS. Forget about the large R or small r limit. It's just linearized modes. You can always perturb around the fixed point.
Last question before lunch.
I'm a little bit confused with these modes that satisfy the nonlinear equations.
Okay.
These solutions are for small rho or are valid for exist for all value of the radial coordinates? Or
Okay, if I don't combine them with the irrelevant operator that will change the UV part of the geometry, they solve the full equations.
Okay.
Okay? And as long as, of course, V and Z are just exponentials. If I have other stuff in V and Z which are not exponentials, things will start going bad. As long as phi remains large and the potential takes this form, these are exact solutions.
Okay. So they are analytic solutions of the system.
Yes, exactly.
That's nice. And is this the way that people find these solutions, or
You mean
like
numerically?
No, analytically, because this is analytic, no?
Well, yeah, I mean, well, there is techniques that you can use and find exact solutions, right? Yes.
Okay, okay.
Yeah.
Well, thank you.
No problem.
Last one? Okay, clap. Be nice and clap.
Okay.